Welcome to the deep dive. Today, we're pulling back the curtain on something you probably use every single day without really thinking about it. Video streaming.
Right. It just works most of the time.
Exactly. But we're not just watching videos. We're talking about the architectural marvel that makes services like YouTube actually function. Specifically, how you'd engineer a really robust real-world application using Kubernetes for something as demanding as, millions of video streams.
It's a fascinating challenge.
It really is. Our mission today is to give you a kind of shortcut to understanding this complex infrastructure. We want to break down how a scalable, resilient, and importantly, secure system could be built, sort of demystify the tech behind those apps you use all the time. Even if you're just starting out with these concepts, hopefully you'll walk away with some surprising facts and practical insights and see how these seemingly huge problems get solved with clever design.
Yeah, breaking it down piece by piece.
Okay, so let's kick things off. The fundamental question. Why even bother with a specialized Kubernetes architecture for a YouTube-like app? What breaks if you don't have one? What's the big pain point?
That's the perfect place to start.
Yeah.
Because a YouTube-like app isn't just big, it's immense. You've got large-scale video streaming, constant user interactions, likes, comments, uploads, and just enormous data storage needs. Without a clear architecture, you hit serious walls fast. First off, scalability challenge.
Right, like a video goes viral suddenly.
Exactly. That kind of surge can just completely overwhelm components if they aren't built to scale dynamically. Then you've got reliability issues.
Yeah.
Say a back-end service crashes while it's processing videos. Without fault tolerance, playback stops, uploads fail. It's bad user experience.
Mm-hmm.
And just managing all the pieces, front-end, back-end storage, caching it, becomes a nightmare. Complex component management without a structure like Kubernetes?
Goose track.
Totally. And that leads to performance bottlenecks. Slow video loading, sluggish UI, maybe slow transcoding because resources aren't allocated right or caching isn't effective, and, critically, security risks. You're handling user data, private videos maybe, without proper measures, you're wide open. Plus, deployment inconsistencies, manual deployments across different environments, recipe for errors.
Okay, so that's a pretty daunting list of problems. Crashing, slow, insecure, hard to manage, not great. Here's where it gets really interesting, though. How does Kubernetes step in and offer, solutions? How does it transform these challenges?
Right, it's not just patching holes, it's a fundamental shift. Kubernetes provides core benefits. First, scalability. It lets you dynamically support millions of users and streams. Components scale up or down automatically. And think about the cost savings there too, scaling down when traffic is low.
That's huge.
Not just handling peaks, but being efficient.
Good point. Elasticity.
Exactly. Second, resilience. It ensures the app stays available even if parts fail, pods crash, networks hiccup. Kubernetes works to keep things running. Third, maintainability. Managing all those services becomes much simpler, much more standardized across testing and production.
Makes life easier for the developers.
Absolutely. Which leads to a better user experience, fast playback, reliable features. And finally, security. Built-in tools and patterns to help protect user data and the videos themselves. And for you, the listener, designing this kind of architecture is really a practical way to learn Kubernetes. You see how deployments, services, storage, all these core concepts actually work in a demanding real-world scenario. Makes it click.
Okay, that makes sense. It provides the structure and the automation needed.
So let's unpack this theoretical architecture itself. What are the main components, the pillars of this YouTube-like app?
Yeah, let's look at the blueprint. Conceptually, you can break it down into four main parts. You've got the front end, that's your web UI, the video player, where users watch, browse, comment, like.
What the user actually sees and interacts with. Precisely. Then the back end. This is the engine. It's the API service, handling user requests, video uploads, doing the transcoding, managing user accounts, that kind of thing. Third, the database. This is where your persistent data lives. User profiles, video metadata, titles, descriptions, tags, comments. Something like PostgreSQL, typically.
Got it. Holds all the important info.
Right. And fourth, the cache. Usually an in-memory store like Redis. This gives you super fast access to frequently requested data think, video thumbnails, user session info, which takes a huge load off the main database, makes things snappy.
Okay, front end, back end, database, cache. And you said each runs as a containerized service in Kubernetes. How does Kubernetes actually, manage these pieces? How does it let them talk to each other?
That's the orchestration magic. Let's take them one by one. The front end runs as a deployment, Kubernetes makes sure you have multiple replicas, multiple copies of your front-end pod running to handle all the user traffic.
So it can handle lots of people watching at once.
Yeah. Exactly. It's exposed internally via a service, usually cluster IP, so other parts of the app inside the cluster can find it.
Mm.
But for users outside, you use an ingress. That ingress is what maps a URL like stream.example.com to the front-end service, letting users access the app. And critically, you set up liveness and readiness probes.
Probes, what do they do?
Good question. They're like health checks. A readiness probe checks if a pod is ready to actually handle requests before Kubernetes sends traffic to it. A liveness probe checks if a pod is still running correctly. If not, Kubernetes restarts it. Keeps things healthy.
Okay, makes sense. Self-healing, almost.
Kind of, yeah. Now, the back end also runs at a deployment, usually with multiple replicas. This handles those video uploads, does the heavy lifting of transcoding videos into different resolutions and formats.
So it works on my phone and my big screen.
Exactly. And it handles all the API requests from the front end. It talks to the database and the cache via internal services. And what's fascinating here is you could even split the back end further into microservices. Maybe one dedicated service just for video processing, another for handling user API calls. That isolates workloads, makes scaling more granular.
More flexibility.
Definitely. Then the database. Since it needs stable storage and a consistent network name, we use a stateful set, not a deployment.
Stateful set. Different how?
Stateful sets guarantee stable, unique network identifiers for each pod and handle ordered, graceful deployment and scaling. Crucial for databases. It uses a persistent volume claim, a PVC, to request and attach storage. This ensures the user data, video metadata comments, all that persists, even if the database pod gets restarted or moved to another node. Data safety is key. And its service usually has restricted access. Only the backend should be able to talk to it.
Right, lock it down.
Yep. And finally, the cache. Usually runs as a deployment, maybe with replicas for high availability. It caches things like video titles, thumbnails, maybe user session data, exposed via a service, so the backend can quickly grab frequently needed data without hitting the database every single time. Big performance boost.
So this whole structure, deployments, stateful sets, services, ingress, PVCs, it breaks down this complex app into manageable, scalable, connected pieces.
Exactly. It makes it understandable. Even for beginners, you can visualize it. Okay, 5 front-end pods, traffic coming through the ingress, back-end processing uploads, talking to the database via its service. It provides that clear structure.
Okay, moving beyond just the individual components, how does this whole setup truly handle, immense traffic, and maybe more importantly, stay up when things inevitably go wrong? This is absolutely critical for something like YouTube. People expect it to just work.
You're right. That's the core challenge at scale. Scalability and resilience. Scalability is about handling the load, whether it's steady high traffic or sudden viral spikes. Resilience is about surviving failures, a server crashing, a network blip, and staying available.
So how does Kubernetes help achieve that kind of massive scaling?
Primarily through horizontal scaling, using something called the Horizontal Pod Autoscaler, or HPA. This is really cool. The HPA automatically watches metrics like CPU usage, or maybe the number of incoming requests per second for your front-end and back-end deployments. If CPU usage goes above, say, 70%, the HPA automatically adds more pod replicas. If it drops low, it scales back down.
So if that video goes viral?
The HPA sees the spike in requests or CPU load on the front-end pods and might automatically scale them from, say, 5 replicas up to 20, or whatever limit you set. It just handles it, then scales back down later to save resources.
Automatic elasticity.
Precisely. The cache can also scale horizontally by adding more replicas. The database, being stateful, is often scaled vertically, giving the existing pods more CPU or memory. Though there are ways to scale horizontally too, it's just more complex.
And what about distributing all that traffic evenly once we've scaled up? We have 20 front-end pods now. How does the traffic get spread out?
That's load balancing. Kubernetes services, by their nature, load balance traffic across all the healthy pods behind them, so the internal traffic between services is automatically spread out. For external traffic hitting your stream, the gamble.com URL, the ingress controller like Nginx or Traefik handles that. It load balances incoming user requests across those 20 front-end pods and can also handle SSL termination, encrypting the traffic.
Okay, scaling handles the load. But what happens when inevitably a server crashes, or maybe just one part of the application fails? How does it stay resilient?
Kubernetes has resilience built in. We mentioned deployments automatically restarting failed pods. That's the first line of defense.
Right, the self-heal.
Yep. And those liveness and readiness probes we talked about are crucial for resilience too. They ensure traffic only goes to pods that are actually healthy and ready, preventing errors caused by sending requests to a struggling pod. Plus, you can define pod disruption budgets, or PDBs.
PDBs.
Pod disruption budgets. They let you specify the minimum number or minimum percentage of pods for a service that must remain available during voluntary disruptions, like node maintenance or upgrades. So if you're upgrading the cluster nodes, a PDB for your backend might ensure that at least, say, 3 backend pods are always running throughout the process. This prevents the upgrade from accidentally taking down your entire backend service.
So it guarantees a minimum level of service even during maintenance.
Exactly. And connecting this to the bigger picture, you need data resilience too. The database stateful set using persistent volumes ensures the data itself survives pod or node failures. But you also need backups. Using a tool like Valero for regular backups of your database, and maybe even your persistent volumes, gives you that safety net against accidental deletion or data corruption you can restore if the worst happens.
So backups are essential.
Non-negotiable for critical data. So putting it all together, scalability features like HPA handle the load, and resilience features like probes, PDBs, and backups ensure the app recovers from failures. It keeps the service reliable for users. And again, these are standard Kubernetes tools you can learn and implement.
Okay, so it scales, it stays up. Now, how do we keep this whole thing secure? And how do we even know if it's actually working well? Performance, security for something with user data and video, these are paramount. You can't mess this up.
Absolutely critical. Security is about protecting the application and data from threats building that digital Fort Knox. Monitoring is your dashboard, your eyes and ears, tracking performance, detecting issues early, knowing if videos are buffering for users.
Let's tackle security first. How does this architecture actually lock things down? What are the key measures?
There are several layers. First, RBAC role-based access control. This is fundamental in Kubernetes. You define roles with specific permissions, like only the backend service account can read and write to the database service, or only certain admin users can deploy new applications. It enforces least privilege.
So not everyone can access everything.
Precisely. Then, network policies. These act like firewalls between your pods inside the cluster. You can create rules saying, for example, front-end pods can only talk to back-end pods on a specific port, and back-end pods can only talk to the database and cache. This drastically limits the blast radius if one component gets compromised. An attacker in the front end can't directly reach the database.
Isolates the different parts.
Yep. Exactly. For sensitive info like database passwords or API keys, you use secrets management. Kubernetes secrets store this data securely, often encrypted at rest, and inject it into pods only when needed, rather than hard-coding it in container images or code. You also need to think about secure images. Use trusted base images, minimize what's in them, and constantly scan them for known vulnerabilities using tools like Trivy or Claire before you deploy.
Catch problems early.
Yeah, shift left security. And finally, for external traffic, TLS encryption via the ingress controller is essential. Encrypting traffic between users and your front end protects data in transit.
Okay, that sounds like a solid set of defenses. RBAC, network policies, secrets, secure images, TLS.
It's about layers. No single thing is foolproof, but together they create strong protection. Even a beginner can start by implementing basic RBAC and network policies. They make a huge difference.
And what about knowing if things are running smoothly? How do we keep an eye on performance? Are videos buffering? Is the backend struggling?
That's where monitoring comes in. You typically deploy a monitoring stack like Prometheus and Grafana. Prometheus scrapes metrics from your cluster node resources, pod CPU memory usage, requests latency, error rates, and application-specific metrics. You can even instrument your app to report things like video buffering times or transcoding queue lengths.
So you can see exactly what the user experience is like.
Right. Grafana then lets you build dashboards to visualize all these metrics, set up alerts if things go wrong, like latency spiking or error rates increasing. You also need audit logging. Kubernetes API server audit logs track who did what when crucial for security investigations, detecting unauthorized access attempts. For runtime security, tools like Falco can monitor system calls inside your containers and alert on suspicious behavior like unexpected network connections or processes being spawned.
Like an intrusion detection system for containers.
Sort of, yeah. And it's good practice to regularly scan your cluster configuration using tools like Kubescape or Checkoff against security benchmarks like the CIS Kubernetes benchmark. Finds misconfigurations before they become problems. And finally, you need clear incident response processes. What do you actually do when an alert fires or a security issue is detected? Who responds? How? Having that plan is vital.
So it's a combination of metric collection, visualization, logging, security scanning, and having a plan.
Exactly. Security prevents the breaches, monitoring ensures performance, and helps you detect issues fast. Both are crucial for trust and reliability. And you can start simply, maybe just with Prometheus and Grafana for basic metrics, and build from there.
So after this really deep dive into the architecture, the scaling, the resilience, the security, who is this specifically for? When should you, listening right now, consider using an approach like this?
That's a great practical question.
Sure.
This kind of architecture is really ideal in a few key situations. First, obviously, for high-traffic applications. If you're building something like a video streaming app, a social media platform, an e-commerce site where you expect a large user base or significant traffic spikes, Kubernetes is built for that.
Makes sense. Handles the load.
Right. Second, for multi-tier applications. When your application naturally breaks down into distinct components, front-end, back-end, database, maybe several back-end microservices, Cache Kubernetes helps you manage that complexity, keep things modular and maintainable. Avoids that tangled monolith problem.
Keeps things organized.
Definitely. And third, it's for production-ready deployments. When uptime, reliability, security, and monitoring are top priorities, when you need a system you can trust for a real business or service, this robust approach makes sense. So if you're building that YouTube-like app with a web player, APIs, a database like PostgreSQL, and you need it to scale for potentially thousands of users concurrently, this is the kind of architecture you'd look at.
Okay. This raises an important question then. For someone inspired by this, wanting to implement something similar, what are the absolute key things to consider? What are the practical next steps to make sure it actually works effectively?
Right. It's not just copy-pasting YAML files. There are critical considerations. You absolutely need scalability planning. Define your HPA rules thoughtfully, set appropriate resource requests and limits on your pods, and test your scaling. Use load testing tools to see how it behaves under pressure before you launch.
Don't just assume it will scale. Test it.
Test it. And resilience testing. Don't just set up probes and PDBs, actually test them. Kill pods, drain nodes in a staging environment, see if the application recovers as expected. Chaos engineering, even on a small scale, is valuable. Security best practices aren't optional. Regularly scan images, enforce RBAC and network policies from the start, encrypt sensitive data everywhere you can, make security part of your development workflow.
Build it in, don't bolt it on.
Exactly. Your monitoring setup needs to be comprehensive. Don't just monitor CPU. Monitor application-level metrics, user experience metrics. Set up meaningful alerts. Know what's happening. Have a solid backup strategy. Implement database backups using tools like Valero or native database tools. And crucially, test your restore process regularly. A backup isn't useful if you can't restore it.
Good point. The restore test is key.
And don't forget cost optimization. Kubernetes can be expensive if you're not careful. Set resource requests and limits accurately to avoid wasting resources. Use cluster autoscalers if your cloud provider offers them. Keep an eye on your cloud bill.
So plan, test, secure, monitor, backup, and watch the costs.
That's a good summary. And for beginners wanting to get started, the best way is hands-on. Deploy this architecture locally using Minikube or Kind. You can use Helm chart to easily install components like PostgreSQL or Redis. Then, try deploying Prometheus and Grafana to monitor your local cluster. It gives you that practical, real-world experience without breaking the bank.
Start small, build confidence.
Precise.
Wow. It's really eye-opening to see how these massive services we use every day are actually put together. It's not magic, it's engineering. What struck me most is how these different pieces, scaling, resilience, security, aren't separate things. They're all interconnected parts of this one system. Designing it this way really empowers you, the learner, to build things that are truly scalable and robust.
Yeah, it's a holistic approach.
And we saw how it tackles those core problems. We started with handling viral surges, preventing failures from cascading, locking down data. It gives you a blueprint for building with confidence.
And what's fascinating here, I think, is how understanding these individual components, the deployment, the stateful set, the service, unlocks an understanding of the entire system. You start seeing how they work together to solve these really complex real-world problems.
And like fitting puzzle pieces together.
Exactly. It demystifies it. So here's a thought to leave you with. As you use services like YouTube or Netflix today, think about the underlying structure. Consider how understanding these building blocks, the front-end, back-end, database, cache, all orchestrated by Kubernetes, doesn't just empower you if you want to build something similar. It fundamentally changes how you perceive and evaluate any complex online service. That seamless experience you enjoy. It relies on these concepts of scalability, resilience, security, ensuring your data and your video streams are delivered reliably and safely. It makes you appreciate the invisible engineering behind the simple click of a play button.
A lot going on behind the scenes. Keep exploring, keep building, keep applying this knowledge. That's all for this deep dive.